6 periods.
Okay.
Oh, yeah. This is roughly.
That's where I was like, oh, I shouldn't be there. Yeah.
Also, last week I gave out derivative and integral rules. Raise your hand if you did not get one of these up. Okay, anyone else? Okay, I'm gonna go through just full housekeeping things here. So your test is going to be split into 2 days, Wednesday and Thursday. Day one, the multiple choice will be 8 questions. And then day 2 will be integral topics, numbers 9 through 16. I'll have the formula sheet attached that you see on the back of your packet. You can use your calculator. I will have help sessions Wednesday and Thursday. So Wednesday morning, I'll go over pages 15 through 18 in your packet, mainly focused on derivative topics, and you guys are welcome to work ahead of time. But I will hold that session 7:15 in the morning, and it'll be recorded. So if you can't join, I'll post it up on my website after the session ends. And then Thursday morning, I'll do on Teams. I'll send out a link through Remind. And I'll work through pages 19 through 22. Okay. I'm not going to check packet this week. I just feel like it's our schedule is so rushed. So pages 13 through 22, I'm going to check all next Monday. Okay, but I encourage you guys to work through the packet. I think the packet will help you prepare. And if you attend those help sessions, you can just, that's part of getting the homework done as well. So, but I'm not going to check those pages until next Monday. Okay, so I'll send out a reminder this Sunday for that. Okay, so multiple choice. I do want to talk about how I'm going to grade it. Okay, so I'm not grading it the same way that AP is going to grade it. That if you just circle the right answer, I'm not going to give you full credit. Okay, I'm looking for work for where work is needed. Okay, so there are some problems where it's just pure calculator and you're just reading it off the calculator. If it's a graph and you're finding the x-intercept, okay, there's not much work you can do, but there's something that requires chain rule, product rule, or use substitution. I'm looking for those steps. Okay, so when you take a multiple choice test, I will remind you to show your work. I'm looking for your work. Now, having said that, I'm also giving partial credit. If you miss a problem, but your work shows that you have some understanding, then I'll give you partial credit. So there's an upside to me looking at your work. I can give you partial credit. So basically, I'm grading it like a free response, but then giving you guys a kind of that feel for what multiple choice could feel like on the AP exam. But obviously, on the AP exam, okay, they're just grading it just by your answers. You don't have to show work on the AP exam. But for me, I am asking for you to show work. Okay, next week we're just going to focus on FRQs, and then I'll print out packets for you guys to help prepare for your AP exam. Okay, any questions for this week that you guys have? So today I'm just going to go through pages 9 through 12. I know you guys already did that for homework, but I want to kind of go through each of the problems as much as I can. Tomorrow, I'll probably focus a little bit on page 13 and 14, some miscellaneous topics. And then if I can't finish what I did on page 9 through 12, I'll do that tomorrow as well. Tomorrow's even shorter. I think tomorrow we only have like 20 minutes in class. Okay. All right, let's go to page 9. Okay, just want to kind of run through these topics. Make sure you guys are good with second theorem that we've been that you see along these pages. I'll just see if you have any questions as we go through these. Okay, so page 9. If you look at number two, we have a height that's suspended from a spring given by h of t. What is the average height? So that's the hint. If you see that word average height, we're thinking average value theorem. Okay, so average value theorem is 1 over b minus a, integral from a to b of my function. And on the test, if you solve this problem, I'm looking for you to show me these steps. Okay, now obviously you could enter this in the calculator and then get that decimal value and compare it with these options and see which one matches. But I'm looking for the steps. Okay, so the steps that's required here, at least for what I'm seeing. Also, if you saw this on the AP exam, this will be part of a non-calculator section. Okay, so I'm giving you the calculator, but I'm asking for work because a lot of these problems are part of the quote or supposedly on their non-calculator portions. Okay, 16 becomes 16t. That's just the power rule. But this I got to go through u substitution. My u value is this pi t over 4. Okay. Find the derivative, I get d over dt equals pi over 4. Cross multiply, and I get dt equals 4 over pi. I make that substitution. Cosine becomes sine. There's a leftover 4 over pi. That coefficient of 7 stays. And as soon as I find my antiderivative, I can now work in the bounds. So upper bound first, minus parentheses lower bound, and I'm multiplying by 1/2 at the very end. So that's going to give me 32 plus 28 over pi, multiplied by 1/2. That's coming from this 1 over b minus a, and I get 16 plus 4 over pi. Okay, number 3. Limit of the definite integral. So this is saying, well, if we're looking at limit, it's like this is kind of a strange notation, right? So, but maybe, okay, so whenever you see a limit of a complex problem, that usually is maybe some variation of a L'Hopital's. Okay, so they're kind of maybe trying to get you to do L'Hopital's rule. But I think the best thing to do is, you see that h in the denominator? Why don't we just rewrite it? If we rewrite it, force it in the full denominator, it feels a little bit more more familiar, right? You have a limit of a numerator denominator. So the first thing we do with limit is we evaluate at our h value. Okay, so replace every h with 0. I get the integral from 1 to 1. Up top, the bottom, I get replacing 0, and for h, I get 0. And look, if you look at the numerator here, the integral from 1 to 1, the bound didn't change. If my lower and upper bound is the same, my integral is always going to be what? 0, right? There's no area for me to find. So this is good. If I see 0 over 0, there's the link, right? Because we see, okay, 0 over 0, limits. Okay, that's L'Hopital's rule. So L'Hopital's rule says, take the derivative of the numerator, separately take the derivative of the denominator, and then reevaluate. Okay, so the derivative of the numerator, I'm putting that notation d over dx to indicate that I'm taking the derivative of this full integral. And this should remind you of second theorem. So back down here, second theorem says, if I take the derivative of the integral, I can wipe those two operations out. The function is going to pretty much remain unchanged. Just have to insert the upper bound into the variable and multiply it by upper bound's derivative. Okay, so we know these two operations will cancel each other out. The only thing we got to do is make sure we insert this 1 plus h squared in for x, and then multiply by h prime, the derivative of 1 plus h, which is times 1. So this not really going to change. Okay, so once you have your numerator resolved, the denominator is h's derivative is 1, and so now we have our updated limit expression. We can reevaluate, and we get 0 in for h. I get 3 plus 1 is 4. Root 4 is 2. 2 over 1 is 2. Okay, so it's a lot of second theorem here. Number 4, the definite integral from 0 to tangent to 0, find f prime. So I want to find the derivative of a definite integral. That's a clue that we want to be able to apply second theorem. But second theorem, you see how your upper bound is the variable and the lower bound is the constant. So I want to get, it just feels a little better, a little easier if I can get these two bounds to match my rule. So I'm going to flip the bounds. So I'm going to adjust the bounds. If I change the bounds, I can do that. I just have to make sure I adjust with a negative sign on the outside. Okay, so I'm going to rewrite the integral, okay, just to make it match my rule a little better. And then I'll take the derivative of this integral. It's asking for f prime. So derivative of a definite integral, we know these two operations cancel each other out. I'm just following my rule here. My rule says my upper bound gets inserted into the function. So tangent replaces t. But don't forget about the second part here. Multiply by the upper bound's derivative. So tangent becomes secant squared. So I'm left with negative secant squared over 1 plus tangent squared. Okay, there's an identity that says that 1 plus tangent squared equals secant squared. Okay, if you don't recall that identity, there's no need to memorize it. And the reason why you don't need to memorize it is because you can always derive it just by using an identity that you all know. Okay, we know that sine squared plus cosine squared is equal to 1. Right, we know this is true. You know sine squared plus cosine squared equals 1. If you don't remember the other identity, you can always do this. You can divide everything by one of the trig functions. So let's say I divide everything by cosine squared. And so you're left with tangent squared plus 1 is equal to secant squared x. So there's an identity that there's one that we can use without having to memorize it, because all we did was we just arrived there using what we all know, sine squared plus cosine squared equals 1. So now that I know that 1 plus tangent squared is the same thing as secant squared, I can replace that with secant squared. Negative secant squared over secant squared is negative 1. So there's my answer. All right, page 10. Okay, page 10 says the graph of a differentiable function is shown. H is the area between 0 and x of f of t. Which of these values can we organize from smallest to largest? Okay, so h of 6 is just the integral from 0 to 6. 0 to 6 is just some area below the x-axis. We don't have to know what the area is. We just know that whatever that number is could be negative 10, negative 16, or negative 10, negative 12, negative 8. We know it's negative, right? Okay, h prime of 6, okay? If I want to find the derivative of this notation here, right? If h of x is the integral from 0 to x of f of t, then that means h prime must be the derivative of what I started with. Okay, so hopefully we recognize the second theorem. We know derivative and integral will just cancel each other out. I'm just left with f of x, because x is going to insert itself into t. So if I know h prime is f of x, is just the graph, and h prime of 6 is just the order pair. We know f of 6 is just whatever that y value is on the graph. F of 6 is 0. So that can do one derivative down. H double prime must mean f becomes f prime. So f prime, we may not know the slope, but we do know that this is definitely a positive slope, which is, so if you're comparing these values, even though you don't know specific values, you know how to order negative, 0, and positive, right? So negative is obviously the smallest value. 0 is next, and the largest value is positive. So we can choose answer choice A. Okay, number 6. Let the function be defined as the integral, definite integral of an expression on which of the following interval is the graph concave down. Okay, so we need to be able to understand that concavity is relating to the second derivative. So I want to make my way to the second derivative. But this is really, f of x is not sitting at this function level, right? It's sitting a level above it. But the nice thing is, if I find the derivative of an integral, I know that those just bring me back down to this 2t cubed that I see here. So if I find the derivative of an integral, the operations will cancel out, and I'm just left with what you see here. This 2t cubed minus 15t squared plus 36t, but the upper bound gets inserted So that's why it gets replaced with x. So that's my derivative. So my derivative is really just this expression here without the integral. Okay. Keep going. I need to find the second derivative. So power rule gives me 6x squared minus 30x plus 36. Okay. Concavity. So let's do our test for concavity. So let's make our second derivative sign line. We set our second derivative equal to 0. Factor out a 6. Continue factoring. I get 2 and 3. Make your sign line. And then you test your values. Test values in each interval here. So test 1, 2.5, and 4 back into the second derivative functions. And then see what the signs you get. Positive means concave up. Negative means concave down. So I want concave down. So concave down, 2 to 3. All right, number 7. Find the derivative of a definite integral. So more second theorem practice here. Upper derivative of a definite integral, we know they cancel each other out. Upper bound gets inserted to the variable, but don't forget, multiply by the upper bound's derivative. So I need a times 2 as well. I need to worry about this times p prime, which is part of my second theorem rule. Okay. Once you apply that, then you're just trying to get it cleaned up to look like one of your answer choices. Okay. Number 8, f of x is given. G is the antiderivative of f, which is another way of saying it is this is my g prime. Okay, this f is really my g prime. So I'm given a starting point. I'm trying to find an ending point. So the way I like to think about this is particle motion, where if I have a given position, I can add it to some displacement and get my final position. So f of b equals f of a plus the integral from a to b of f prime. So I'm adapting it for this problem. And the rest can just go in the calculator here. We know g of -1 is -2. I want to bridge that gap between my two x values. So take the integral from -1 to 3, make the calculator do the work for us there. And we can add the decimals together. We get 2.255. Okay, number 9. If f is a continuous function, then the integral from 1 to 4 of lowercase f of root x in terms of uppercase f. So we're going to have to go through a little bit of use substitution because of the parentheses, but we're just basically going to involve first theorem because we know that lowercase f integral will turn to uppercase f. So first thing we do is let's go through use substitution for what we see in front of us. We always target the parentheses as our u value, and our goal is to replace the root x and replace the dx. Okay, so we let u equal to the root square root of x, which is x to the 1/2. Go through power rule, 1/2 x to the -1/2. Do a little bit of cleanup, 1/2 root x. Cross multiply, solve for dx. Dx equals 2 root x du. So we make our substitution. Root x gets replaced with u. Dx gets replaced with 2 root x dx. Sorry, du. And here the advantage is, okay, my root x goes away. I can pull the 2 out in front, and now I have a clean integral rule, integration problem with everything in terms of u. So we know that the relationship is lowercase f turns into uppercase f. So lowercase f becomes uppercase f. 2 tags along. Right? We want to evaluate the bounds. The bounds, however, is in terms of x. So we have the antiderivative. We bring the original variable back, and it's just plug in the upper and lower bound. F uppercase f of root 4 minus f uppercase f root 1. Root 4 is 2. Root 1 is 1. Keep the coefficient out in front, and we're able to make it look like one of our answer choices. Number 10 feels like number 8. We'd like to use this formula a lot. Final position equals initial plus displacement. You have your integral of velocity, that's your displacement. Position is 4 at time t equals 0, so that's your anchor, that's your starting point. And you want to find x of 1. Okay, so the first thing we do is we need to figure out when is velocity equal to 0. Right? We want to figure out when is velocity equal to 0. So you set velocity equals 0, and then you can make the calculator find the x-intercept for you after you graph it, or do numsolve, and you get 1.379. So that's what you want to do. You want to find out where is location, where's the particle located at 1.379. So that's where I want to end up. I'm starting at 0, so I got to bridge that gap between 0 and 1.379. Make the calculator do the work for us there. We get negative 1.533. So we're starting at 4, we're moving backwards 1.533 units, and we're going to end up at location 2.466. You can see that number 11 has the similar format. We can use this position equals final equals initial plus displacement and adapt it for different derivatives. We can make it a velocity version as well. We can say ending velocity equals initial velocity plus displacement of acceleration. So I can just shift everything one derivative down, and I still have a formula that I can use. So I'm looking for v of 3. I know what v of 0 is, and I just have to figure out what is that change in velocity from 0 to 3. Okay. Make the calculator do the calculation for us. We get 6.7. So velocity is 5 plus a change in 6.7 velocity. We add that together. Velocity at 3 must be 11.7. Okay, more use substitution. But for number 12, if you look at your answer choices here, your answer choices is all in terms of u, which means that I have to adjust the bounds to be in terms of u as well. So I have to learn how to use that 0 and 9, insert in for u and solve, insert in for x and solve for u. So my bound is in terms of 0 and 3 because my answer choices is in terms of u. Okay, so tomorrow we'll go through pages 13 and 14. And then Wednesday is your multiple choice day 1 quiz. And then Thursday is your integrals quiz 2. I encourage you guys to continue working through the packet to prepare for the test, but I won't check your homework until next Monday. Have a great day, guys. See you tomorrow. Thank you. Good day. Good day. Hey.
I think I'm ready to take the test for the
Differential equation. Okay.
but
You come out from school someday, or you can come in for series. 4th or 5th series, but they're just an hour.
I think I have a class.
Okay.
Yeah, it's business.
All right, sounds
Can I
good
do
tomorrow.
Wednesday?
Yeah.
Because I have the EOC tomorrow. I don't want to.
Yeah, that's fine.
Okay.
Okay.
I finished.
Okay, great. Thank you.
Thank you.
This is last week. I was missing like the whole packet. So.
Okay. All right. Okay, great. I can do that. Thank you. Yeah. You're gonna have to come in fourth or fifth day. Because at least there's an hour block. Right, but we'll still have these days. Those nights should still be. I see, no, Friday. Yeah, you should be safe. You still have 45 minutes. Yeah, so. So you can Thursday and Friday.
I have time.
Oh, actually, let me,
A
hold on.
lot of hope.
Guys,
I did not. It was so nice. I had a lot of hope at halftime that this might actually tie the game. And then Everton got robbed of a penalty.
Huh?
I said then Everton got robbed of a penalty. Stonewall penalty. And then Deepak Reed did sub one. Dude, it's just a league. Origi against Everton. It's just not fair. He is with the bike assist. No, but Origi was involved in the first goal. He stood up so long. Dude, at halftime, I was really sitting with my dad. I was like, Liverpool could tie this game, man. And then I found it funny how Allison. Bro, I did too. It was fun. But like, oh, it's that game that could have.
Yeah, that's really good. Yeah.
Do they just talk about like how the exam would be kind of get confident on?
They just do reviews over.
Yes, you could build it.
They're really good instructors, but they don't know what exactly the condition. But they didn't know a lot.
Well, here's the thing, really good. The last game was last Tuesday. Yeah, a whole week. We had like 2 days. No, but you guys have to go to Newcastle. And that's not going to be easy. Newcastle went from 19th to 9th. They were 19th up there. So.
Yeah, sorry. Most of us,
I mean, I know. In my head, it's either going to be like 6-0 or it's going to be like. Or it's either going to be close or it's going to be absolute blowout. There was never going to be. But that was a stonewall. Yeah. It was behind. Y'all got lucky. Y'all got lucky.